Ugh, I wish I could do that.
I'm never going to be able to score a strike. Gary would be so disappointed in me.
Let's go, guys.
Hey, look what I found.
Well, you should watch it. Have you ever wanted to bowl like a pro?
But you keep getting a gutter ball.
Well, we have a secret. Come closer. It all has to do with physics.
And it starts with something you're all familiar with. The bowling ball.
You might think a bowling ball is the same throughout, but really, the interior of a bowling ball is not uniform. Bowling balls are weighted. In its core, under the hard outer shell, is a weight block. There are two different basic weight block shapes, asymmetrical and symmetrical. The shape and placement of these weights affect the center of mass of the ball, and it affects the spin and curve of the ball as it rolls down the lane. If the ball is a uniformly solid ball, the center of mass would be in the middle, making it easier to roll down a straight line. But, since the weights shift the center of mass depending on their shape, the ball will start rolling to the side as it spins down the lane. This tilts the rotation axis. This is called precession. When the rotation axis tilts, the ball will spin to the side of the lane.
But how does this help us bowl a strike?
Well, let's continue our investigation in the lab.
Whew. What's the question again? How does understanding the inside of a bowling ball help us bowl a strike?
Oh, right. Understanding how the interior of a bowling ball affects its motion can help us assess where and how to aim the ball. There are two ways for a ball to roll down a lane. In a straight line, or on a curve. You might think that bowling in a straight line will be better because you have more control of your aim. But that's not all that goes into bowling a strike. In reality, bowling on a curve will yield much better results.
Before we throw the ball, let's analyze the bowling lane. All bowling lanes are oiled, but they can be oiled differently. Depending on how much oil there is and where it is placed, the coefficient of friction is different. Where there is more oil, the coefficient of friction is less. The coefficient of friction determines whether the ball will go down the lane in a straight or curved path. When you bowl in a straight line, the bowling ball starts sliding down the lane, but then friction causes the ball to spin as it approaches the pins. On the other hand, when you curve the ball is spinning throughout. If a bowling ball rolls on a curve, it hits pins on an angle, which makes it easier to get a strike. You want to hit between pins 1 and 3 for right-handed people, or 1 and 2 for left-handed people, an entry angle of 4 to 6 degrees. This angle distributes the impact evenly throughout the arrangements of pins.
The curve also causes the bowling ball to move on a horizontal drift across the lane. This means that if you are bowling in a straight line, you should roll the ball down the middle of the lane. But if you roll your ball on a curve, you want to start rolling it on the side of the lane just before the gutter.
Notice how the bowling ball moves across the lane diagonally from where he is standing.
So why is curving the ball really different than bowling in a straight line? The equation for rolling friction is Fr equals mu r times n, whereas Fr is the rolling resistance force, mu r is the coefficient of rolling friction, and n is the normal force.
The coefficient of rolling friction differs from the coefficient of sliding friction because the coefficient of sliding friction depends on the texture and surface of the objects, whereas the coefficient of rolling friction depends on the radius of the rolling object, the depth which the object sinks, and the toughness of the surface. Rolling friction is created by the small indentations that form as one object rolls across another.
In rolling friction, the reason the bowling ball slows down and eventually stops is caused by the deformations created when the bowling ball and the lane are compressed.
How you bowl is only part of being a good bowler. Another thing that's very important is what you bowl.
The equation for torque to find the curve T equals F times R, where F is the force of friction and R is the radius of the ball, shows us that the less friction there is, the less torque. That means that it is harder for the bowler to curve the ball. Since you want more friction, you need a heavier ball, which would help create a bigger curve. Also, since delta E equals F times D, the more distance the ball goes, the greater the change in energy. The change in energy is affected by friction, which changes kinetic energy into sound and other kinds of energy. So, if there's a greater change in energy, that means there's more friction to the ball, causing it to curve.
And that's it! Wait, is it? I feel like we're missing something.
Well, we talked about the bowling ball and the lane, but what about the pins?
How would studying the pins help us bowl? Don't you just have to knock them down?
No! The pins are just as important in the game as the ball. If we understand how they are built, we can understand the outcome of our bowl. A standard pin is 15 inches tall. Looking at a bowling pin, it seems bomb heavy. We wanted to see if that was true, so we decided to find the center of mass. In order to calculate the center of mass, we used a Riemann sum. We found ordered pairs by taking the height and radius of the pin and plotted them on a graph.
A Riemann sum finds the area under a curve by breaking it up into shapes like rectangles and then finds the area of each of the rectangles. To avoid overestimating or underestimating too much, we used a middle Riemann sum by moving the rectangles up half a step. This is the equation we used to find the center of mass.
We used a spreadsheet to do all of our calculations. Our calculated center of mass is about 0.16 meters up the bowling pin. However, the official regulation center of mass of a bowling pin is about 0.134 meters up the center of the bowling pin. So our percent error is about 24.2%.
This is a high percent error, but we attribute this room for error in our data. The way we graphed and visualized the pin must have been off. A real bowling pin has more mass towards the bottom than our data calls for. A possible explanation could be that either its base is wider than we thought, or it's weighted at the bottom. If we were to do this again, we would get our hands on a real bowling pin and use gravitational force vectors by hanging something like a plumb bob and using gravity.
When we look at the dimensions of a bowling ball, the radius of a bowling ball 13 pounds or greater is 0.108 meters. The bowling ball makes contact with the bowling pin 0.027 meters down from the regulation center of mass. Since it makes contact below the center of mass, it is more likely that the bowling pin will topple over than be pushed straight back.
But to maximize your bowling strategy, you should know how much force to use on the ball. Since our equation for torque, T equals F times R, is the distance an object is hit from its center of mass, the R equation is 0.027 meters. F is the force of the bowling ball on the pin, so for more torque, you should throw the ball with more force.
So let's head back to the bowling alley. So there you go. The secret to bowling is physics.
Now go and use your newfound knowledge and bowl.
You'll be getting strikes in no time.
Wow, that was really helpful.
And super informative.
It's really great we found it. I can't wait to go bowling again.
Hello, kids! What are you guys up to?
Oh, nothing. Just watching the movie you got us.
I've never seen that before.
Then where did it come from?
I like to go bowling with my friend Bert, with my bowling ball and my bowling shirt. I like to roll the ball down the lane. On a good day, I'll throw a few strikes, maybe some spares, that's what I like.